All right, can everybody hear me? Good. Okay, my name's Paul MacDougal. And I'm going to talk on an introduction to Arduino programming. My daytime job is a design engineer at NVIDIA. I have a degree in computer graphics, PhD in computer graphics. So I'm kind of a software guy. But my hobby is embedded programming, Arduinos, Raspberry Pis, things like that. Home automation, a little bit of robotics. So today I'm going to talk to you about Arduino programming. So I'm going to tell you a little bit about what Arduinos are, what they can do, and then we're going to go through a little case study of a bicycle speedometer. If you've been upstairs to the exhibit, you may have seen my table with the bike on it. And so that's the project that we'll be discussing today. Arduino is an open source platform consisting of hardware, software, and programming tools. So there's a picture there of an Arduino board. It's about the size of a credit card. You also get software and programming environment in which you can write your programs and download it to the boards. Being open source, not only software but also hardware, means that the schematics, the designs of the hardware is available to the public. And the Chinese have jumped onto that, and you can now get Arduino clones for $8.60. There's also an IDE, an integrated development environment. It runs on Mac, Linux, Windows. It's free to download, and that's where you do your programming. You write your sketches, what they call them, sketches, and download them to the Arduino board. And the big, great thing about Arduino is that there's this really large, active community of people worldwide that are willing to post their source code, their experiences, and share with other people. So if you Google Arduino and just about any other word, you're going to find some hits, somebody that's already done it, and they can get you kind of kick-started on a project that you might be working on. Arduinos are these small processors that can read inputs from switches, temperature sensors, pressure sensors, velocity sensors, microphones, GPS modules, and on and on and on. So you can read all kinds of inputs about the world, and then you can generate outputs to drive displays, to display motors, servos, send tweets to the internet. And all this stuff is using code that other people have developed and packaged up into libraries that you can download. So part of the title, at least in the official program, is embedded. So what's an embedded processor? So it's not like the processor in your PC at home or your notebook. Think more of like your microwave oven. Inside there's a little processor. It reads the touch panel. It controls the clock. It controls when the oven turns on and off. Or a washing machine or a dishwasher. They all have little processors in them now. And that's the kind of programming we're talking about. So when you download the IDE, there are a list of examples. One of the first examples that people look at usually is called Blink. On the Arduino board, pin 13 is connected to an LED. So if you set up pin 13 as an output and turn that pin up and down, it'll blink the LED. So here's what the program to do that looks like. At the top, we define a constant that has the value 13. And that tells us which pin we're going to be using that the LED is hooked up to. And then there are these two routines in red there, one called setup. Setup is called one time at the beginning when the processor boots up. And then the other one is called loop. And that's called over and over and over and over and over. As long as the processor is powered on, it'll keep calling loop. So for the one-time thing in our setup, we say, okay, we want to configure pin 13 as an output pin. And we're going to be sending signals out that pin to turn the LED on or off. And then inside our loop, which is going to be called over and over and over, we're going to write to the LED pin a value that's high. And that turns the LED on. And then we're going to wait. We're going to delay 1,000 milliseconds. A millisecond is a 1,000th of a second. So 1,000 milliseconds is 1 second. So the light stays on for 1 second. And then we write the pin to low. LED goes out. And then we wait another second. And then the loop routine gets called again. So it goes high, waits for a second, goes low, waits for a second, and then it gets called over. So the LED just blinks on for a second, off for a second, on for a second, off for a second. So you would type this in or copy it from the examples, download it to the board from your PC or whatever that you're using to program the board. And then you can unhook the PC, and whenever that Arduino boots up, whenever you apply power to it, it'll call the setup, and it'll call loop, 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 loop. So the thing will, even if it's not hooked up to your computer, the board will blink that pin. All right, so we're going to look at a project for building a speedometer for a bicycle. I'm going to use a very common design pattern, which is sense some inputs, analyze those inputs to compute some kind of result, and then respond appropriately to those values. So what we're going to do is we're going to sense the wheel rotation. How long does it take for the wheel to make one full revolution? From that, we're going to compute miles per hour, and then we're going to respond by displaying that value on some kind of a display. Okay, so we're going to use a reed switch. Reed switch senses the presence of a magnetic field. If you've ever had a home security system installed, they put reed switches on the frame around the door, and they put a little magnet on the door. And when the door is closed, the magnet is nearby and the reed switch closes. And when the door is open, the magnet's no longer there and the reed switch opens up. And so there's a short video here. Played my first part of the slide. Let's see if I can get to it. That's not good. We won't replay the video. Right, while that's starting. Okay, so we're going to use the Arduino to monitor that switch, and the switch is going to pull a pin on the Arduino to ground. So the switch is normally open, and when it gets closed, it's going to connect a circuit from that pin to ground. And when a pin is grounded, and you read it as an input, it reads as low. When it's not connected to anything, it's floating. It might read high or it might read low, you don't really know. And so what we do is we use a resistor. Let's start here, you can watch the, you can see the little fingers in the reed switch. As I bring the magnet close, they close. Oh, that's not good. Okay, so the Arduino's going to sense the switch closing, and it's going to calculate how long it takes for the wheel to make a full revolution. And then once we know how many milliseconds that took, and we know how big the wheel is, we can compute the miles per hour. Sorry about this. Okay, so we time how long it takes the wheel to make one rotation. We know the circumference of the wheel, which is pi times the diameter. And so pi times d divided by t is inches per second or inches per millisecond. We do a little bit of conversion, 60 seconds in a minute, 60 minutes in an hour, 12 inches in a foot, 5,280 feet in a mile, and you end up with miles per hour. And then we need to display it somehow. I chose to use a 7-segment LED display here, and there's a library already available that you can download and access. Okay, so I started talking about how we hook up our reed switch. So there's a switch to ground, and when the switch is closed, it pulls that pin down to low. When it's open, instead of letting that pin just float, we use a resistor to pull that pin up to a high value. So it's high when the switch is open and low when it's closed. So we saw this sketch outline previously. There's the setup routine and the loop routine. We're going to choose pin number 2. There are about 20 pins on an Arduino. You can use any of them for either input or output. And so I'm going to configure pin 2 as an input with this pull-up resistor enabled. And then I'm going to call another function that I'm going to write that will set up the display appropriately. And then in my loop, I'm going to call a routine that's going to sense how long it takes to do the wheel rotation and return that value to me as an integer. And I'm going to pass that into a routine that will compute the miles per hour. So I'm going to return that as a floating point, which is what this double means. And then I'm going to call a routine that I write that says display the speed on the display with the miles per hour as an input. Right. So now we'll look at some of those other routines that I was talking about. So to set up the display, that requires 3 wires between the Arduino and the display. And then what we do is when this routine display setup, we call lc.shutdown false, which means bring it out of sleep mode. So we're now powered on. And then I decide to display my name on the 4 digits. Luckily, my name happens to be letters that work well on 7-segment displays. If your name was Mary, it's hard to make an M on a 7-segment display. So that was something that, as it boots up, I see my name, I know that things are working. 2 miles per hour routine. I calculate this constant up the top. I have a 24-inch wheel, I've got pi, I've got my conversion constants to go from milliseconds to hours, and from inches to miles. And then I have to be careful not to divide by 0 because that's not well defined. And so I take my constant divided by the milliseconds and return that. So that's a pretty simple routine. And then to display the speed, I need to take that miles per hour number and I need to pull out something for the hundreds digit, something for the tens digit, something for the ones digit, and something for the tenths digit. I didn't figure anybody was going to be driving their bicycle more than 999 miles an hour. So if you're going 1,000 miles an hour, this code probably won't work. And I kind of left out the details on how to actually put it on the display. And now for the hard one, okay? Sensing the wheel rotation. So we have this pin that is normally pulled high, and each time the magnet goes by the switch, okay, the contacts close, the pin goes low, and then as the magnet moves away, the switch opens back up and it goes back high. So we're looking for a high to low transition. Every time we see that high to low, we know that the magnet has come close to the switch, and so we want to find 2 of those and measure the distance, the time between them. So we expect when we call in that it will probably be, the magnet won't be at the switch, and so it will probably be high, but there's a chance that it might be low. And so to make sure that we don't start counting in the middle of a pulse, the very first thing we do is, while the switch is reading low, we just keep reading it until it goes back to high. And then we wait for the first switch closure. So while it's high, we wait. Is it high, is it high, is it high, is it high? And then suddenly it goes to low. And so that's that first falling edge. And we record the time, the start time. We wait for it to go back high, and then we wait for it to come back low a second time, and that's our end time. And we return the difference. So here's our ideal behavior. If we happen to end up starting while it's low, we wait there, we wait for it to be high, we record the first falling edge start time, we wait for it to go back high, we wait for the second falling edge, and that's our end time, and we return the delta there. Alright, so we designed how we wanted to do it, we coded up Now let's see if it works. But here it is on a bike. You might have seen that it said Paul. I spun the wheel. It says I'm going 0. It doesn't work. That's the way engineering is. If first time you fail, you say, okay, I'm done. Engineering's probably not for you. So try again. So we did something wrong. We need to test a little bit and figure out what we did wrong. And of course, slides with videos don't seem to work very well on this version of PowerPoint. Okay, so it turns out that reed switches, when the magnet comes by, they go like this. They close, but these are mechanical things. And after they hit, they kind of bounce. And so instead of getting one nice falling edge, it goes down and it bounces open, so it goes back high and it shuts. And then it bounces again, and so you'll get a couple little pulses. And so what I was timing is how quickly those multiple pulses in the bouncing was happening, not a full rotation of the wheel. And since those all happened in the same millisecond, the start time and the end time were the same. And so I got a value of 0 milliseconds to do a rotation. So this is a picture from an oscilloscope, which is a way to visualize this invisible stuff called electricity. And you'll see it was high, and then it went down low, and it bounced back up to high, and it went back to low, and did a couple more intermediate bounces. And so the real world is dirty and messy, and so you have to account for that. And so we do what is called switch debouncing. It's a very common thing that all engineers know about. And I knew it was there, and I knew it was going to fail, but I want to show you that things don't always work quite the way you think they do. And so you can debounce either in hardware using additional circuitry, or you can debounce in software. And so what we do is we can measure how long that switch bounces for, some number of milliseconds, and then we're just not going to do any reading while the switch is bouncing. We'll let it stabilize, and then we'll start reading some. So I've added 2 more lines to our routine for doing the wheel rotation calculations. And so for 10 milliseconds, I'm not going to read. I'm not going to do any readings. I'm going to do it once as we get that first falling edge, and I'm going to do it again as we do the rising edge, because it can bounce at both of those transitions. So I just went by the video. We'll play it in a minute because I don't want to crash again. But now it works, and the version you see upstairs in the exhibition is that one. If you give a mouse a cookie, does anybody get that reference? You do? One? Anybody else? He's going to want some milk. Give him some milk, he's going to want a straw. So it's a kid's book. So, enhancements. Right? What are the things that we can do to build on this basic system that we've already built? So one of the first things that I wanted to do is I don't like where it says 0, 0, 3.7 miles per hour. So we can suppress those leading zeros. Can we record the fastest speed? Sure, we can. Every time we measure a speed, current speed, we can compare it against our fastest speed that we've seen, and we can save that. Can we record distance? Can it become an odometer as well as a speedometer? That's a big change. One of the things that you may have noticed in the design is that when I go to read a wheel rotation, I wait for 2 rotations. So I get the first one, so I know that I'm at an edge, and I wait for the second one. If you go upstairs and you watch, you will notice that the display of your speed updates not every time the wheel goes around, but every time the wheel goes around twice. Okay. Now, if you are, if you want to be an odometer, you have to make sure that you get every revolution counted, right? In my speedometer, I can totally ignore the wheel, go measure 2 rotations, and give you a speed. So to be an odometer, I'd have to change it so that I make sure that I get every revolution, and then I can measure the time between revolutions, and I'll be able to update the speed every revolution. Odometers in your car, they don't lose how far you've driven when you turn the ignition off. They remember it from trip to trip. So keeping track of how far you've gone this time is not that difficult, but when you turn the speedometer off and come back the next day, you need to remember how far you've driven on all your previous trips. You can do that with an Arduino. There is non-volatile memory inside the chip that you can program and write your current odometer reading. You have to update it each time the wheel goes around, because you don't know when they're going to turn the power off. And then when you power back on, you can read that number and restore your odometer, your lifetime. And so that adds complexity. Change the brightness of the display. That red LED is not particularly good out in sunshine. So there's lots of things we can do, and each one of these. Another thing, so if we want to become a speedometer / odometer, we need to be able to choose which mode we're in. Okay. Are we showing the speed, or are we showing the distance? Okay, so now we need to weigh. We could just show the speed for a second, show the distance for a second, but most likely you're going to want to switch. But if the user can push to toggle between the 2 modes. And so now, not only do you have to watch the wheel and make sure that every rotation, every time that magnet goes by, you're there watching, so that you can count it. Okay? Now you also have to watch this switch that a user can push at any time. So now you're having to watch 2 things constantly, and that requires like a total rewrite of that sensor wheel position routine, because that sensor position rotation routine has, while it's high, keep reading the pin, watching, and waiting for it to go low. And so it's stuck in that tight loop, watching that one pin, and it's not watching any other pin that the user might be pressing the button on. And so you have to say, is the magnet there? Is the user pressing the button? Is the magnet there? Is the user pressing the button? So now you have to do both of those concurrently somehow. So you have to change the way you do the programming. So what I presented works great for one function that it's designed for. But as we add just a little bit, it doesn't seem like it's a big new feature. It totally causes us to have to rewrite our software so that we can watch multiple things. Okay, so I'm about done. We don't have too many people. I'll be happy to answer some questions. I'll go back and try to run this video. I have not. Some of the wires aren't quite long enough to the display. I ordered on Amazon 5 meters of 10 conductor ribbon cable so that I can get it up front where I can watch it. It's dangerous to drive with this. Network cables. So I do have a home network, and I use a Raspberry Pi as the overall control, and it talks to the cloud when I want to. So I have my rain gauge, for example, and the Raspberry Pi sends the current rain reading out to the cloud. But I have Arduinos situated here and there in my house. One controls my cat feeder and my garage door to tell whether the garage door is open or closed. Another one controls the drip irrigation system and monitors the rain gauge. I have plans for others near my air conditioner where I can measure the temperature on the high side and the low side of the compressor and some other things like that. Okay, so your standard Arduino board has two ways to do it. The most common way is to use the USB cable hooked up to a PC running the IDE. There's also a little 6-pin connector right over here. It's labeled ICSP, in circuit serial programming. Okay? So that's a different way to program. There are a number of boards that have come out that have either Wi-Fi or Bluetooth interfaces that allow you to program them doing that, and some of them the IDE is hosted in the cloud somewhere, and so you save your program in the cloud, and it talks to your device over Wi-Fi, and it programs it, and magically it starts running the new program. Other questions? Right. So you can buy what are called shields, which are like daughter cards that plug in to the, there's a row of connectors here and one at the top that hook into those I/O pins. And so people have designed, say, an Ethernet shield. Okay? It plugs in, it uses a subset of the pins, and it has a chip that knows how to talk Ethernet. So you can plug it into your Ethernet and hook it into your router, your home network, and whatnot. And then there'll be a library of software that allow you to act as a little web browser, host, web server. So you can buy Ethernet shield, a Wi-Fi shield, a Bluetooth shield, a motor controller shield, a servo shield, and you can build your own if you want. Yes, you had a question?
So how are you currently
my project upstairs currently has a 9-volt transistor battery. And this right here is power jack. I think you lost audio go. So you can power it from the USB cable. I think it's that I understand. So you can power with the USB cable, or you can plug in power. Power it with that.
So the DC bring this up to life. And then power source of the battery. Maybe some build itself or
You could hook up a generator, like they do for the headlights. I'd have to do that. Any other questions?
are all the inputs just straight high-low or?
Good question. No, they're not. So the 14 on the top are digital, which is high-low. The 6 at the bottom are analog. So you can configure them as digital, high-low, or you can have them read a voltage, and it'll give you a number between 0 and 1023. So it's a 10-bit analog to digital converter hooked up. Oh, one thing I wanted to, some people have asked, so what's the difference between an Arduino and a Raspberry Pi? Pretty common question. So the processor on a Raspberry Pi, on the original Raspberry Pi, is probably 40 times as powerful as the processor on an Arduino. And the new Raspberry Pis have 4 cores, and they run even faster. So 4 times 50, so it's probably 200 or 300 times as powerful for doing computations. So if you have something that requires a lot of computation, you probably want to use a Raspberry Pi. They both have very, very large user communities, and if you Google Raspberry Pi and almost anything else, you'll get hits. The Raspberry Pi does not have analog to digital converters. So you either have to get your own and hook up to it with an I2C interface or something. Or there are some tricks for doing RC circuits to fake it out. The other main difference is that the Raspberry Pi is running Linux. It's running a full operating system. The Arduino is running your program, and that's just about it. So you're in full control. If you have things that are timing sensitive because you have to generate a waveform that drives a servo exactly right, the Arduino is great for that. If you try to do it on a Raspberry Pi, it'll work most of the time. Every once in a while, you'll get glitches and stuff because Linux decided this is a good time to see if the hard disk needs service, or see what time it is on the internet, or any other thing that this multitasking operating system decides it's time to do.
Have you used any of the TI boards?
Have I used any of the TI boards? So there are a fairly large number of companies that have these kind of processors. They all have development boards that they want to sell to people or give to people so that they develop products with them and end up being big customers. They have their own development environments. Some of them are free, some of them you have to pay for. They don't have the large user community that Arduino does. And so there are advantages to some of these other boards. If you want to do capacitive touch input, the TI boards are really great for that. But you've got to learn a whole new development environment. If you want to Google TI and something else, you can have fewer hits. So I don't. I use pretty much Arduino and Raspberry Pi.
The CI came to our university, and same thing you're saying, that they have a small market share, but TI's the rise. TI's coming on the bandwagon now, while it's here, and all kinds of marketing about TI.
Right. I work for NVIDIA, and we make a development board called the Jetson TK1. One of the first robotics teams mentioned that they were using it for vision. And so I was all happy when it came out. But I started using it, and I was fighting Linux. Everything I wanted to do required a Linux update this, and so it wasn't any fun, so I stopped doing it. Even though my company makes it. A lot of people now take their chip and put it in this form factor, and they port the Arduino IDE so that you can take all these programs that run on Arduino and then they'll run on their chip. And so, well, that's good. Why not run it on Arduino? It costs $8. And an Intel Edison that costs $30 or something. There are reasons. Other questions?
More for me, so board may be different.
Another good question. There are, so even from Arduino, the official Arduino, there were a series of releases. This is the Uno. This one has a DIP processor. It's a Atmega DDR 328P. So there are different versions. To be Arduino compatible, you kind of have to have this form factor that the shields can plug into. Okay? You can use the processor comes in a couple of different. Comes in the DIP version. It comes in the surface mount version. There are smaller ones that are even less expensive than the Uno. There are ones with more capable processors. There are ones with less capable processors. Atmel also makes AT Tinys, which are very small processors. That package, I think, has 28 pins. They make one that has only 8 pins. And so you get power, ground, reset, and you have 5 pins left for I/O signal. But that chip costs like 80 cents. And so if you have a project that only needs a couple of I/O pins, design your own board, get one of these processors, you can still program it with the same IDE. So and if you need to go the other way, if 20 pins isn't enough, there's an Arduino Mega, which has 54 input pins, even output pins. Anything else? All right, thank you. I invite you to come upstairs and see the actual bike.